So what we're going to do is think about our antiderivatives and some practical meaning for them. And what we're going to do is we're going to think of, I'm going to take a couple functions to start with. Let's just take linear function f of x equals 3, and here's the origins of this. Here's the line y equals 3. And first off, let's think of taking the integral or finding the antiderivative of 3, and what that will equal is 3x, and we'll think of plus c. But for now, let's just think about this 3x. That's the antiderivative. And checking the derivative of 3x would be 3. Now, how we're going to think of the antiderivative now is an area under a curve. So here's a curve, this line y equals 3, and here we can find the area under it. So let's say we take the value x equals 5. If we find this area in here, this shaded area, what's the area? Well, it's length times width. It's just a rectangle, so we've got 5 times 3. So this area between 0 and 5 equals 15. And if I think of starting at 0 and going to 5, well, so the antiderivative was 3x. Well, the area here is 3 times that x value, 5. Now let's take, say, another line. Here's the line x equals 3. Between 0 and 3, what's the area under the curve there? Well, it looks like length times width, 3 times 3, or 3 times that x value, or 9. So here it seems if we can find the area under the curve by finding the antiderivative. The area will be 3x. So if I chose x equals 7, the area would be 7 times 3, 3 times 7, 3 times x, or 21. X equals 4.5. We get an area 3 times 4.5. So we can see that the area under that curve is the antiderivative. Let's take another function. F of x equals 2x. So graph that function. Straight line, slope of 2. Let's think of the antiderivative. Antiderivative of 2x dx. This ends up being x squared plus our constant. But again, let's focus on this x squared. Again, checking the derivative of 2x, or derivative of x squared is 2x, so x squared would be the antiderivative. So let's take some points on this line. Let's take this point right here, say x equals 3, y equals 6. And we want to find the area under that curve. This area starting at 0 going out to x equals 3. This area above the x-axis, what's the area there? Well, the area looks like it's a triangle, so 1/2 base times height, or in this case 1/2 base times height equals 9. So when x equals 3, area equals 9. Well, that's just 3 squared, or x squared. What happens if we take the point, let's say, let's clear some of this out. So we take an x value equal to 5. So we've got the point up here, 5, 10. So x equals 5, and now we're looking for the area under this curve. It's triangle, 1/2 base times height, 1/2 the base times the height equals 25. X equals 5. 5 squared is 25. So again, we see that this area under the curve, so between 0 and the x value above the x-axis, the area is the antiderivative. Well, what happens when we get a more complicated looking function, say x squared? If the antiderivative is going to be 1/3 x cubed. We can check that. 3 times 1/3 is 1. Reduce the exponent by 1. The derivative of this is x squared. Well, now we come to a situation where we've got our parabola, and let's say we choose some point here. We've got the point 39, and we want to find this area under the curve. Based on what we've found so far, it would seem as if, I'm taking a value of x equals 3, the area under this curve between 0 and 3 should be 1/3 times x cubed, or 9. Well, how are we going to figure out whether that area is actually 9? We can't very well. It's got curves, so we can't really. We don't have a nice, easy formula for a triangle or a rectangle or a trapezoid or anything like that. So how do we find this area? Well, here's where we use what's called Riemann sums or Riemann summation. So let's take a close-up look at this graph. So let's say this is our parabola, and here's our point 39. We want to find this area. The idea behind the summation, or approximating this area, what we want to do is we're going to draw just little rectangles. They're not all going to be perfect because obviously a perfect rectangle is not going to quite fit. But if we have the bases all the same, we can come up with something. So I could come up with a. Boy, I really got myself stuck here. Now I have to finish off all these rectangles, don't I? But the idea is you've got little pieces that are above, but you're only making an approximation. So So we could create an approximation such as this. So we've got, let's just take this side of the parabola, roughly drawn. Here's our point, 3, 9. Here's a line, 3. And maybe we could take, so here's x equals 2, x equals 1. Make one here, make one here, make one here. All right, so we've got these little rectangles. We're missing some space, but we're only doing an approximation, so it doesn't really matter that much. Okay. Now, you notice with this one, this top one, I've got a lot more rectangles. What ends up happening, so if we maybe zoomed in on one little tiny piece of the parabola, say this is x equals 3, and here this might be 2.999. Okay, so so we're looking at some little tiny area right up here. The graph is actually curved, but since there's such a small distance between these two x values, what ends up happening, kind of what we looked at when we were talking about limits, is the h gets very, very small. You get something that almost looks like a straight line. Okay? And I've exaggerated this curve just to show that it's still a parabola. But really, when you get this close in terms of x values, you almost have a little tiny straight line that you can barely tell what the curve is. And so what we can do here is, we can draw all these little tiny rectangles, etc., etc., all the way up to here. We've got one here. And now, if I'm making this approximation, all these little areas, we saw these little areas. Let's take a little zoom look. Blow this up, and we can see, okay, here are all these little places where we're missing out. On top of these little rectangles, there's this little space. As the rectangles get narrower and narrower, so here's our parabola. Here's x equals 3. Here's x equals 2.999999999. Okay. Again, so we have a really tiny space. You can still make a bunch of little tiny rectangles. And what ends up happening is, the space between the rectangles, which we can find an area. You can always find the area of a rectangle, width times the height. But the little missing space in the approximation gets smaller and smaller and smaller and smaller. So the idea behind the Riemann sum is that you've got these tiny, tiny, very, 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 very narrow rectangles that you're finding the area of, and that's how you're determining what the area under this curve is.